Alright, this is our section on 7.1 and 7.3, which is the law of sines and the law of cosines. So what these two laws are, this is actually a generalization of everything we've learned so far for right triangles that will apply to any triangle. So you see I've just got some arbitrary triangle down here that's not 90 degrees. However, these formulas still work for a right triangle, which is pretty cool in a way. So the way they work, law of sines, it relates. You normally only use two parts of this at once. Like you may use, that's a little thicker than I wanted. You may just use these together. The angle A, angle B, side A, and side B. And the way it works, you see I've got four variables there. I've got the two angles and the two sides. And if let me change my pen here. Okay. If you know two of the angles and one of the sides, well, we know uppercase A, we know uppercase B, and we would know one of these two sides. Let's say we know side A. Then we've got an equation that we can solve. We've got a formula we can solve for that one unknown, that lowercase b that we don't know. So that's typically how it works. If we'd been given side C and angle C instead, we would just do those two, right? Maybe so if we're given angle B, angle C, and one of these sides, like you're given side C, you use these two. But you could also compare A to C. I mean, these rules work however you want, as long as you have the side on top and the sign of your angles on the bottom. Or, just to make things more exciting, you can flip the whole thing upside down, and these ratios still hold. So we'll do some examples, and this should be pretty easy to do. The law of cosines is for a different case. This is when you know two of the sides this time and the angle between them. So it's important that it's the angle between them there. Okay, and it would also work if you just know all three sides. So down in these formulas, each one of these relates the three sides. So like say this first one, for example. Sasha. Sorry, the dogs are going nuts. Sasha, what are you doing? There you go. There you go. Come here. Okay. Now calm down. Alright, so going back to these formulas, sorry about that. Looking at the first one, for example, we have side A, side B, and side C. Right, so we've got the three sides there. That's the other two of the sides appear again in the formula. B and C each appear again. Right, but it's the same B we've got over here, and the same C we've got over here. And this we would use this variation to find angle A. Right? If you're given the three sides. However, if you have the two sides and the angle between them, you would use the formula that includes those two sides. So if, for example, we knew side A and C, there we go, and we knew the angle between them, which in our case is capital B, so we would use this second version of the formula that has that side A, side C, side A again, side C again, and then our angle B. So nothing exciting about these formulas. They're pretty easy to do. as long as you're plugging everything into the right place. But other than that, this is just like a calculator exercise. Okay. So let's get going. Oblique triangles, again, just a little more about them. The three sides and the three angles of a triangle, which are the only 6 things you can know about a triangle, really. They can be found if you know at least one side and any other 2 bits of information. That's actually kind of an interesting side note. I should have made a slide just for this. It doesn't work if you don't have at least one side. You have to have at least one side. Why wouldn't 3 angles work? Why couldn't we just have 3 angles? Why not 3 angles? And if you think about it for a minute, you can probably figure this out. Why not 3 angles? And I'll come back to this at some point, if I remember to, and tell you why 3 angles wouldn't work. But I imagine you can piece it together. It's a fun little thought exercise. So this is to help familiarize you with some language. I don't personally care if you know these things, AAS, ASA, SSA, SAS, whatever. If you took geometry, you probably had some teacher drilling this into your head, but it's just not hugely important. The way these are written tells you kind of what you have. For instance, AAS means I have 2 angles, and then I have one of these other 2 sides over here. Either I have this one I've been given. They could have just as easily put the 224 over here. But what this means is we don't have this side. We don't have the side in between the 2 angles. That would be ASA. In ASA, we have the 2 angles and the side between them. So if you've got a diagram, you can figure out pretty easily what you have. Anyway, in case you see this terminology, and you will, our textbook uses it a lot. This is just an explanation of what all these words mean and an illustration. So this is a really nice reference I found in a different textbook. That I thought was pretty nice. So this is our textbook. They mention the different cases you can break this down into based off of what's known. Like if you know a side and then 2 angles, or if you know 2 angles and the side between them, you would use these techniques. Case 1 is not too bad. When you know 2 of the angles, part of it's really easy. This line, this is always my go-to. If I have a triangle and they give me 2 sides, I'll always look for that 3rd side right away, even if I'm not asked to, just because you probably had this drilled into your head in geometry classes, algebra classes. This is pretty common knowledge. Hopefully you're pretty comfortable with it at this point. But if you've got 2 of the angles, like you have A and B, it's real easy to plug those in and then find the unknown, find C, right? Just subtract each of your angles A and B from 180. So that's super nice. And then you just use the law of sines for your other 2 angles, or for the other 2 sides. So super straightforward, probably my favorite case to work with. These other 2 both involve law of cosines, case 3 and case 4. And you're probably wondering what happened to case 2. I'll come back to that at some point. Okay. Actually, I'll go ahead and say that now. You notice we skipped over section 7.2. Right, this is 7.1 is this case 1. 7.3 covers case 3 and case 4. That missing case comes from that section we skipped, 7.2. And it's something called the ambiguous case of the law of sines, which is, I don't know, it's not that complicated. It's just something I don't want to waste a lot of time on. The idea is it's possible when you're using these formulas to sometimes get 2 angles and you don't know what to choose. And you have to spend some time kind of figuring out which angle actually would make a triangle, which one wouldn't provide anything useful. So we just kind of skipped over that. We're only going to talk about the nice cases that work out well. Okay, so what do I want to say here? For these cases, you've got to pay attention to, for case 3 and case 4, you've got to pay attention to which angle you're using which formula for. And it's annoying. I can never keep this straight. I always have to look this up when I'm doing it. So it's not something I expect you to know. I say that. I think you could probably memorize this for one test. I'll think about that. I may actually give you some note about that on your exam. But anyway, in this third case, you've got to find the smaller of the two angles using the law of sines. And this last case, when you know the three sides, you've got to find the largest angle using the law of cosines. So there you go. When it comes to finding sides, you could use that law of cosines with no problem. It's when you start trying to find your angles, that's when things get complicated. You want to use the smaller angle. You want to use the law of sines for the largest angle. You want to use the law of cosines for. If you don't have to, I try to avoid the law of cosines to avoid having to remember this, which one goes where. But I do know that a lot of physicists use use these two laws a lot. So if you know you're going to have a heavy physics background for your major, you may want to spend some more time focusing on when to use each of these two cases. Okay. So again, just another recap. There's the law of sines, which we're about to cover. So typical problem, solve this triangle. We've been given our angle A, 32 degrees. We've been given angle C. Oh, I've got angle B labeled. Here, I'll fix this really fast. That didn't work. There, I'll change this into a C. This C into a B. There. So I've got angle B here. Okay. And I've got this A. Okay. So, what do we need to do here? This is angle, side. That's something that we use the law of sines for. Conveniently written for you here. We just plug in all of the things we know. Oh gosh, I hope I have that on the slide. Oh, I do. Fantastic. So here I've plugged in all the unknowns. Now you could go ahead and start punching this in your calculator. What I normally do is I would go ahead and get rid of this sine of 81.8 degrees by multiplying. That didn't work very nicely. So let me write out what exactly happened. I'm going to multiply both sides by this sine of 81.8 degrees. But if I multiply this side by that, I also have to multiply this one. I don't know if I'm going to have room for this. There, I'll just cram that in there. So over here, we're multiplying and dividing by this sine of 81.8 degrees. That gets rid of it and leaves us with just side B, which is our lowercase b. So there is what I just did, written a little bit nicer, all in one nice pretty equation. Now that's where I would plug it into my calculator. Be careful, a lot of calculators you're going to have to put in parentheses here. It may open up a set of parentheses and you just have to close it up. Just be careful with that. Okay. And we get the calculation of 80.1 degrees. 80.1 centimeters, sorry. So that was side B. So we've still got some unknowns. We've got angle C. How can we figure that out? Well, I would use the fact that 32 plus 81.8 plus this unknown C has to add up to 180. And then the only thing we'll have left is this side C. We can find that using well, I guess we can use the Pythagorean theorem. We're going to have to use the law of sines again. Okay, so here we are finding our angle C. Right, I'm just going to take 180 and subtract the two known angles from it. And I get 66.2 degrees for that. Okay, so now I've got all three of my angles. Oh gosh, I forgot what our other side was. I want to say it was 80.1, but I'm not confident enough to write it, so I'll just leave that. Okay, so then we're going to use our law of sines again. So we're comparing side A to angle A, our newly found angle C to this unknown side C. Okay, that's a terrible 66 there. I don't think I'm making it any better either. Oh well. So we plug in everything we know. Again, we multiply. I'm not going to write it all out this time. We're going to multiply by this sine of 66.2. And this is going to end up right there on top of the 42.9. Boom, and there it is. Okay, and then we calculate that, and that was our final side, the 74.1 centimeters. Here we go. Alright, Kirk Daniel wishes to measure the distance across the Gascogne River. He determined that C equals 112.9 degrees. I wonder how he did that. Well, he figured it out somehow. Angle A is 31.10 degrees. And side B, 34.76 feet. So this is actually something you could do reasonably with a scope of some kind, or even a protractor and on a compass, I guess, or just a compass. If you were at one of these sites C, he measured like due west across your river, and like you had some tower or something in the distance, you could measure the angle between these 2 points, like whatever visible landmarks you've got. You could find the angle between them, like he's done. Find C. And then you could go up, you could take yourself a little walk up here, up to that landmark, and sight in your other landmark. Sight in your two landmarks here and figure out that angle. So this is actually something you could reasonably do. If you're trying to figure out how wide the river was, you could count your steps and figure out how far you are between A and C. And you could measure these angles, again, with your compass. But anyway. Sorry, I always get sidetracked by that. First, find the measure of angle B. Well, that's easy. We know angle A. We know angle C. So I know I can just take 180 and subtract those two. Boom, and I've got 36 degrees. Very nice. 36. Okay. Now use the law of sines to find the length of side A. Again, because we had two angles and the side in between them, we can use this law of sines. So we had angle, side, angle. There it is. There are all of our numbers kindly plugged in for us, including that 36 degrees we just found. This time we got to multiply by this, to get that moved over here up on top of our fraction. So just a tiny bit of algebra there. And then we've got something we can plug into our calculator. And we get 305.5 feet. So there we go. So we could go further, we could have solved the whole triangle, but in that case we're really just trying to figure out how far across the river we are. So another nice example, I just love these real world examples. If you've ever been to a heavily forested area, we've still got some of these fire towers out there. They're a lot of fun to go climb up into, and no one really, I never had anyone say anything about it. We used to go camping in those when I was a kid, go up there in the fire tower, and anyway, they're a lot of fun. My mom actually worked as a ranger fire spotter for a while. She said it was a very boring job, and she's glad it kind of got phased out because people just had to sit in these towers all day and wait for a fire, and it doesn't happen a whole lot unless you're in California, or I think Tennessee had a lot of fires recently. But anyway, sorry. So these things, we know how far apart they are, and that would be typical if you're building your towers. You would want to know how far they are apart so you can do these calculations easily. We find this fire, and again, we take a bearing to that landmark, using your compass, using a compass, and we've got these two bearings here. Okay. This is kind of, a little silly. They took a bearing from north. What we really want is this angle here. But they tell us that these two ranger stations are on an east-west line. What they're telling us, is that this is directly east and west here, this line, or the bottom of our triangle. And since north would be going up 90 degrees, well, this distance here is just going to be 90 minus 42. Similarly, over here, 15, that's on this side. It's on the right side of our northeast here. If we wanted to know the full angle, this time we would have to add 90 degrees to it, right? Because that little section there is 90 degrees. Okay. And then once we've got that, we've got angle, side angle. When you have that, you can use the law of sines. Okay, so we find the angles, and this is such bizarre notation. I understand that trig books use it, but this is just ridiculous. The measure of angle BAC. Yeah, whatever. Angle A. We're going to call this angle A, like we've got it labeled. A is 90 minus 42, and that gives us this 48. And over here we have to add 90. Again, this is just ridiculous notation. We've got angle B here, 90 plus that 15. Okay, so that whole angle there is 105. I know it's messy. I was trying to draw on both sides of that north. I mean, that's this whole angle here. So both the 15 and that added 90. Angle C, the last angle. We take 180 and we subtract our two angles. We subtract the 105 and the 48 that we just found, and we get 27. Oakley dokley, now that we've got our two angles, which are not written in this slide for some reason, what was this one? 48. And this one was 105. And we just found C. Oh, what was C? Where am I getting this 110 from? Oh, that was the length of the side. Okay. 27. There it is. Okay. So now that we have our three sides, we would take, or sorry, our three angles, we would take one of the sides and the angle opposite, and we would relate that to one of our other two. Now, because I knew this was going to be an issue, I was careful reading that last side. They want the distance from this west tower, don't they? I thought for sure it said west tower. Well, I guess we're going to do east tower because that's what I've done what I've calculated here. If we wanted to find the distance from this east tower, we're talking about this tower over here on the right, we've got to look at angle B. Okay. Oh no, okay, now I see what's going on. Gosh. Now I feel really silly. They do want the distance from the west tower. I knew I'd read that right. They want the distance from this west tower. But in order to find this distance, which we're calling lowercase b, we have to use this angle across from it. We got to use angle 105. Okay. So we're going to relate 27, which we're given, to 110 with our other angle here, 105, to find our unknown. What I normally do is I say whatever my unknown is, I want to put that on top of my fraction. So my lowercase b, I want that to be on top. So I'm going to use the version of the law of sines that puts the sides on top and the angles on bottom. So that's what I've got written for you here. Right, you could have just as well put the angle on top, but unless you're finding, sorry, you could have done these, you can always do it flipped upside down. But that's just going to make the calculations more difficult for you because your unknown's down there at the bottom. Okay. That's not even a C. There we go. So we could have done that one, but since our unknown is down here, we would have to do a lot more work to solve this for side B here, this lowercase b. As it is, we plug in everything, and then we take the sine of 105, multiply to move it over here, which is just what we've got, and plug all that in the calculator. Whew. And that was it. Okay, law of cosines. Fun fact, yeah, I already mentioned this before. That this is really cool because this works for 90-degree angles as well. So when these formulas, when you look at a right triangle, so one with a 90-degree angle in it, then this law of cosines is just your normal Pythagorean theorem. This is how mathematics discovery actually works. We have something, this has been known forever. We've known this for thousands of years, this Pythagorean theorem, but it took a long time to generalize that to this case that works for things that are not 90 degrees. Right? So this Pythagorean theorem came first, and then after that someone figured out, hey, we can do this for any triangle with a little playing around. Throw in the cosine of the angle rather than just assume that there is no, what is it, minus 2ab cosine of c. Okay. So solve this triangle, and this time we're going to be using the law of cosines as part of our attack. So when I've got two sides and the angle between them, I want to use the law of cosines for that. So I've got side B, I've got side C, and I've got this angle in between them. So I use the formula that has B, C, B again, C again, and then angle A, the side in between them. Plug it all in, and this is super straightforward. Just plug all that in your calculator. Just again, be really careful with parentheses. You know, every calculator is a little different. You should be able to plug that in and get 10.47. Then you can use law of sines for the other ones. Yes, this is what I was mentioning earlier. Excuse me, we want to use the law of sines for the smaller of these two angles. If we use it for the larger one, this is where things get tricky, because I wonder if I can draw this picture well. Sometimes we'll have two answers. Like if the angle is 60 degrees, well, the sine of that angle is the same as the sine of 100 and, was it 20 degrees? I can't remember my reference angles. So you have two possible triangles, one of them with an angle of 60 degrees. But if we'd used 120 degrees, which is more like that, it is still possible to come up with a triangle from this. Look at this. So if we'd chosen that other value, that other angle that had the same sine value, we could still make a triangle from that. We wouldn't be sure if this was the right triangle or if this was the correct triangle. So we wouldn't know which triangle to use. That's that ambiguous case that's in 7.2 that we're not talking about. Okay. So the way to prevent problems like this from happening or any other errors, we want to just make sure we're finding the smaller of the two remaining angles. Well, how the heck do we know which one is which? It's actually super easy. So here's the side we just found. So of these three sides, we just found the smallest. Which is the next smallest? That is the next smallest. And then finally, C is the largest. So the smallest side is across from the smallest angle. So our smallest side is across from this smallest angle. So this is the smallest. Okay, this next one, our next smallest, I'm just going to call this the medium one. Oops. The medium angle is very conveniently for us located across from the medium side here. And then finally, the largest is this angle C, because it is across from the largest angle. So super easy to tell which one is which, because they're always opposite of their counterpart. The smallest angle is across from the smallest side, etc. Okay, so we want to use the law of sine to find the smaller of the two remaining angles. In our case, that would be this B, this medium angle. Since we've already figured out the smallest angle, we move on to the next smallest. Okay, so we want to find angle B. So let's find angle B. So this time, since I want to find the angle, you notice that I'm using that flipped version of the law of sines. Okay, and I plug in my two sides, 10.47, 12.9, and the one angle I know. And I have to do a little bit of manipulation, but it's the same thing I've been doing. I'm going to multiply both sides by 12.9. Just going to cram that in there. Over here on the right, the 12.9s cancel. We've got sine of B equals all this mess. How do we solve that? Well, we take the inverse sine function. Well, I didn't do that here, did I? So we take, we calculate all this on the right. and you plug this in your calculator as B equals sine inverse of all that mess. 12.9 times the sine 42.3. And I apologize for how messy this is. Trying to draw with a mouse is a lot more difficult than I thought it was going to be. I actually bought a pad that I could write on with a pen and it would be digitized, but it never worked. I sent it back and they said it's been too late. It's been over 30 days, we won't take it back. So sorry about that. So that's how you plug that in your calculator. You should hopefully get 56 out of there. To find your third angle, once we have this 56, life is much easier. We can find C really easily by taking 180 and subtracting the other two angles. Get 81. Okay, and now we can find that one piece of the puzzle we don't have, this side C. Right. So here's that thing we were just talking about. We don't know if we use the other side, if we use the law of sines to find our largest angle, we would have gotten two possibilities. One is almost a right angle, 81.7. The other one is the supplement of that angle, just a little bit past that. Oops. Yeah, this is actually an easier way to say it. The supplement of that angle. I always say the angle with the same reference angle, but that's what a supplement angle is. So we wouldn't know which one of those made up the triangle, and we'd have no way of knowing, which is strange. Okay, let's see. To find angle B to the nearest degree for the truss shown in the figure. Okay, so here we're given three sides. When we have three sides, we use the law of cosines. It's a little bit more annoying to solve this thing. Of course, I didn't actually solve it. I just wrote that it's solved, which is kind of frustrating. But this is just a little bit of algebra. We subtract a squared, we subtract c squared, we divide by this negative 2ac, and that should do it for us. Right, so we subtract a squared, we subtract the c squared, and you notice that doesn't look nearly like what we have. Well, these have just canceled. But now I've got positive b squared, negative a squared, negative c squared. But when I then divide it by this negative, that changes all my signs, and I get a positive a squared, a positive c squared, and just the negative b. So our positive b squared went from negative to negative b squared. So once we've got it like that, plug in all our numbers, calculate it, and we've got the measure of our angle B. 33. And that's it. Thanks for watching, and I'll see you next time.